TPA3255 post-filter feedback. If you look at the marketing, Internet is full of advantages of post-filter feedback, and in forums, confident users are saying that post-filter feedback is so good, and everyone should use it, otherwise the board is crap. With a post-filter feedback, you get so much better results. And let's look, how does it work in reality? Is it so good as it advertised? And here I took Texas Instruments application report. It was done in the same time when chip has been released, and here is a good white paper about how to implement post-filter feedback, written by Dan Kisling and Matthew Birdsworth. They created this document. What is written here in abstract? Class D audio amplifier families deliver high audio performance with less than 0.01% total harmonic distortions and noise to clipping. The high level of audio performance makes this device ideal candidate for high resolution and high fidelity audio application, which previously could only be achieved by Class AB amplifiers. No, nice advertisement sentences. Class D audio amplifiers can be further enhanced by adding additional post-filter feedback or post-filter feedback loop. This application report shows one optional implementation of post-filter feedback for the TPA3255 amplifiers. Filter feedback offers many benefits, including lower output noise, improved total harmonic distortion plus noise performance, improved intermodulation performance, low output impedance, frequency response less affected by load impedance, and suppression of non-linearities of the LC filter. And so, if you copy this particular sentence, it seems post-filter feedback is so good. And anyone who implements such kind of board will copy this sentence. It's written by Texas Instruments. We'll refer it. It will be correct sentence for a marketing, but how it is in real life. And here is this principle. Here you have a chipset. Here you have input, and here is output filter, and we are taking feedback from output filter with specific a combination of resistors and capacitors and giving back to the input, and then we gain some benefits out of it. So if you look at a real implementation and we want stereo bridged configuration, we need 4 such circuits add to chip. Also we need 4 additional operational amplifiers in a buffer cascade, and then we also need a buffer operational amplifiers to drive those, because we need perfect stability here, so minimum impact from the source. Our design become more complicated, and also those elements should be close to chip. That means those are beneath heatsink, and heatsink temperature could change from 25 degrees to 90 degrees. That means all those components should be stable, special requirement to the components, and then this system will work. Especially it's about capacitors. When you use ceramic capacitors, probably we need to use really good and precise capacitors to ensure that system stability and parameter stability. And here manufacturer gave recommendations what those components should be, and for each of those chips, those are different, and so we are interested in TPA3255, and you can see all those components mentioned here. As long as those are filtered components, those should be precise, temperature stable, etc. etc. Also, once we are taking signal from the output, we need additional stability, and here Zobel network is must to ensure system stability. Those electronic circuits provides like a load equivalent on high frequencies. If we have no load condition, still those are working more or less to load the filter and don't allow that filter has a high peaks. What manufacturer is writing about those circuits? The Zobel network helps attenuate a high-frequency ringing by damping the amplitude response of the output of the LC filter and lowering the quality factor Q. It is especially required for open load stability, what I mentioned. Open load stability, no load situation. And here also manufacturer makes the recommendations how much post-filter feedback should be applied, and there are numbers which are working. And now what we are gaining? LC filter distortion. I will not read all that, but if you have a bad inductor, for example, here is a bad open filter inductor with a high non-linearities, you can reduce it by that factor. But let's be critical. It is much better to take a better inductor, and this is no post-filter feedback situation, and we are at much better situation than here, even with a post-filter feedback. Yes, we can reduce some total harmonic distortions from 0.006 to 0.003 or 0.002. Are we gaining here something? Here is our hearing threshold. Theoretically not important. What conclusion we can take? Let's select a good inductor, and then we have excellent amplifier. We don't need post-filter feedback. So it's not solving bad inductor case. It's a little bit improving, but it's better to take a good inductor from the good manufacturer. One thing what I think is important and really worse for some cases that all effort what we need with post-filter feedback, output noise, and it reduces output noise by half. So this is good output noise situation. This is excellent output noise situation. And when we need it, for example, if your tweeter has a horn loaded with a sensitivity 100 decibels, then you may hear a hiss. And when you implement that post-filter feedback, then you will not hear a hiss at all, or almost at all. But for majority cases, when we are using standard tweeters, it's not important, because this noise is already low. It's already low. But there could be cases when it is important, and then yes, you can choose it, despite of all lowlights that we have is post-filter feedback, what we will be looking further. And then in each case, you a little bit improve. And here, for example, signal-to-noise ratio and dynamic range ratio, you can improve it for 5 decibels. But honestly, the human hearing limits are 95 decibels. Here we are already above human hearing limits. Should we go further? Yes, we can put in specs that it's better. But for a listening experience, it's not important. And that's for all those parameters. We can a little bit improve. And also here is standard total harmonic distortion picture versus power. Yes, we can little bit improve. But also, this is human hearing's threshold, and here we improve, and they put in a marketing booklets, and then in reviews we can take that picture and say it's so much better. It's inaudibly better, and it's the same here. It's the same here. We have a slight improvements that comes with a significant rise of complexity of the amplifier. Everywhere, some slight improvements, and then we come to the, let's say, lowlights. Stability analysis. When we introduce that post-filter feedback, our system becomes unstable, and we should really make it in a correct way to have a necessary stability. And there are plenty of tests what should be done with the stability, and once this for that implementation, Zobel network is must. And there is also calculations for a minimum resistor power, what we use in Zobel network for a high power, and for TPA3255 a minimum is a quarter watt, but I would even put a half watt resistor for a worst case scenario when you want to test it with full power sine wave. And someone is testing, there will always be some guy who will test at a full power sine wave at 20 kilohertz, and then you can burn the Zobel network. And there is a note for actual audio. There is a less energy in higher frequencies at 20 kilohertz. Full scale sine wave is very rigorous test. For most audio applications, Zobel resistor will dissipate very little power. So, but we always have some extreme guys, and they will test to the maximum and say that this born burned. So we need to put resistor what can withstand any guy. Stability testing, there are a few tests that should be performed for any post-filter feedback configurations. Test overshoot for a square wave input, test frequency response at full scale. So when you introduce this post-filter feedback, your system could become unstable and you really need to test it. And this is why you need a stable, good, high-quality components. If you test it at one temperature, you should also test at a maximum temperature. And there is a note, overshoot for square wave input. The TPA3255 amplifiers family has integrated feedback loop for noise suppression, which make frequency domain gain and phase analysis for post-filter feedback stability near impossible. You need a special way how to evaluate. Further complexity is added since post-filter feedback loop includes the phase and amplitude characteristics out of the output LC filter. There is internal feedback loop where the internal feedback loop doesn't. For this reason, time domain overshoot analysis is the best means for assessing stability. So it's not so simple with post-filter feedback. It introduces a lot of additional challenges and reduces system stability. And then our guidelines, and what you do, you put a pulse signal and evaluate this post-filter feedback overshoot. I will show you one more picture. And here is a frequency response at full scale. And you can see even with post-filter feedback for different loads, you have overshoot. And I saw some measurements where this frequency response is kind of flat up to 20 kilohertz, because normally it shouldn't be flat. And it is done by correction circuits in a buffer amplifier. And it is kind of so-so solution, yeah. Then you can say there is a drop and there is a peak and then it's additional drop. This is how it is solved in budget amplifiers. So, but generally speaking, those post-filter feedback amplifiers should have some extra brightness. Because in reality, all those errors are included in feedback loop, and it should be done with a cautious. There is really some kind of optimum way how to implement. And then you have all those gain. If you make everything right, your system is okay, and you gain those small benefits. As I said, they are always those are small benefits, relatively small benefits, I would say. Most of them are inaudible. Yeah, most of them are inaudible. Yes, there is improvement. And I would say all this complexity, what you add to your system, you need more operational amplifiers. You need high quality components here. You can't save on it. Your costs are rising significantly. And I personally see only one case when you really need a post-filter feedback. It is when your speaker system has high sensitivity, like a horn-loaded 100 decibels sensitivity tweeter mid-range. And mostly for tweeter. Then yes, then it pays back. But it comes with significant costs and system stability. And this is one answer why most of boards doesn't have it. If you really want to gain maximum out of post-filter feedback, there is another technology. And here is next generation post-filter feedback. I would say what needs a different chipset. And finally, results of the company engineering team work led by CTO Patrick Bostrom are being implemented in the latest conductor topology, ICC5 integrated circuit. In Patrick Bostrom's own words, the conductor, this is a brand name of this post-filter feedback new technology, are nested negative feedback system with two integrated stages, where both stages take feedback from output of the filter. LEDs, poles and zeros are selected so that each stage, as far as possible, only works for correction to errors, not absolute gain of the modulator, which by itself is a very smooth first-order slope. Okay, there are a lot of specific words, but if you simplify this post-filter feedback, that final gain is minor and system stability is excellent. For the marketing, yes, you have new messages to put it, and everyone in forums, in media, especially in YouTubes, they are using that post-filter feedback terms, but not everyone has read all the document, and I really understood that there is something what you gain and there is something what you lose. So we should wait for a next generation chipset when such principles of topology will be introduced. And here is that system architect from IcePower, CTO Patrick Bostrom, who is working on this technology with his team. And then also Bruno Pozzes, and I think he also has been working with that approach for his product's further development. So it's not that simple with post-filter feedback for TPA3255. It's more complex task, and there will be next generation of TPA3255, whatever the name will be or a code will be, where that new trend or new principles will be implemented, and I think those patented principles will be introduced there, and then it really makes sense for post-filter feedback. And it happens that all that external complexity and precision will integrate it in a chipset. Here is IcePower new ICC5 audio chipset, and look, only 8 terminals, and this is where this technology will be implemented, and then we have another life for our products. They will be simple, and those will be very well sounding, and those will be load independent, and so many advantages will come in the future. Not yet in the market, I haven't seen a product with this chip, but there are good breakthrough for the future. And summarizing, after reading this document, my personal opinion, there is no reason to go for post-filter feedback except when you want to differentiate your product in the market and mostly use it for marketing messaging. I hope those IcePower described post-feedback principles will be implemented in a new generation Texas Instruments products as well, and then all complexity will be hidden inside the chipset and we'll enjoy the perfect result out of it. Yes, post-filter feedback has a future, but current way how it is implemented in TPA3255, for me it's not acceptable. Too many drawbacks and too little gains.